Now the topic that I am going to start is simple harmonic motion. First, knowing about simple harmonic motion, periodic motion. Periodic motion means any motion that repeats itself at regular intervals of time. Any motion that repeats itself at regular intervals of time is called periodic motion. All periodic motions are not simple harmonic, but all simple harmonic motions are periodic motion. What actually is a simple harmonic motion? We simply call it as SHM. According to the definition, simple harmonic motion means a periodic motion in which an object moves to and fro about its mean position such that acceleration directly proportional to displacement and acceleration is always directed towards mean position when the motion is said to be simple harmonic motion. The best examples for simple harmonic motion are the vibrations of atoms in a molecule, the oscillations of a simple pendulum, the oscillations of a loaded spring, etc. In detail, I want to explain simple harmonic motion. For example, take a simple pendulum. Simple pendulum means a heavier metallic bob, a small bob which is made up of a metal, a heavier metallic bob which is suspended by means of a massless inextensible string is called simple pendulum. The point from where the pendulum is suspended is called the point of suspension. This center of gravity of the bob is known as center of oscillation. The distance between point of suspension to the center of oscillation, this distance is called length of the simple pendulum. So forget about all these things. I want to make you know what actually is a simple harmonic motion. For example, consider this simple pendulum. The pendulum is initially at rest. When the pendulum is pulled towards one of the side, either maybe towards the right side or left side, when the pendulum is pulled towards one of the side and released, it oscillates to and fro about its main position. For suppose the bob of the pendulum has reached this extreme position. Let this is displacement y. After reaching one of the extreme position, the velocity of the bob becomes equal to 0. As the velocity of the bob becomes equal to 0, the bob behaves like a freely falling body. It then tries to move under the influence of gravity towards mean position. So after reaching this position, the bob tries to move towards mean position. As the bob is moving towards mean position, the bob is moving under the influence of gravity. As the bob is moving under the influence of gravity, the velocity of the bob gradually increases. As the velocity of the bob gradually increases, then what happens? Acceleration of the bob will be towards mean position. So this is the direction along which displacement is given to the bob, and this is the direction in which the bob is having acceleration. Acceleration and displacement, they both are acting in opposite direction. More is the displacement given to the bob, more is the acceleration gained by the bob. That means displacement and acceleration, they both are directly proportional to each other. So what are the three conditions here? First, the bob is moving to and fro about its main position. Second condition, acceleration is directly proportional to displacement. The third condition, acceleration is always directed towards mean position. As all these three conditions are satisfied, we can say that this simple pendulum is said to be executing simple harmonic motion. For any body to satisfy simple harmonic motion, all these three conditions must be satisfied. First, the motion must be periodic, the body should move to and fro about its mean position, acceleration is directly proportional to displacement, which is always directed towards mean position. Then we can say that the body is said to be executing simple harmonic motion. In this case of simple harmonic motion, force is directly proportional to displacement but acting in opposite direction. This force is called restoring force. What is the restoring force? Any force which tries to pull the body towards mean position is known as restoring force. Okay. In case of simple harmonic motion or in case of simple harmonic oscillator, as I told you just now, that a restoring force is directly proportional to displacement. If you remove the proportionality, F is equal to some constant k into y. From that, k is equal to modulus F by y. Here k is called force constant or spring constant, which is defined as the ratio of restoring force to the displacement. K is called force constant or spring constant, which is the ratio of restoring force to displacement. This is in case of a linear simple harmonic motion, but in case of a angular simple harmonic motion, restoring force is torque, which is directly proportional to angular displacement. If you remove the proportionality, we get some constant c into theta. Here c is called torsional constant. From this, c is equal to minus tau by theta. This torsional constant c is defined as the ratio of torque to angular displacement. Here ratio of restoring force to linear displacement. In case of angular simple harmonic motion, the ratio of torque to the angular displacement. As I told you just now that a restoring force is directly proportional to displacement, I can write in case of a linear simple harmonic motion, F1 by F2 is equal to Y1 by Y2, and in case of angular simple harmonic motion, I can write tau 1 by tau 2 is equal to theta 1 by theta 2 in case of linear simple harmonic motion and in case of angular simple harmonic motion. Next, for a simple harmonic oscillator, acceleration is directly proportional to displacement but acting in opposite direction. Just now I told you while explaining the concept of simple harmonic motion. From this, if you remove the proportionality, we get some constant omega square into y. Here omega is angular velocity. From this, I can write a plus omega square into y is equal to 0. This acceleration is nothing but d square y by dt square plus omega square into y is equal to 0. This is in case of a linear simple harmonic oscillator, and moreover, according to the relation between acceleration and displacement, since acceleration directly proportional to displacement, therefore I can write a1 by a2 is equal to y1 by y2. This is how acceleration and displacement, they both are related in simple harmonic motion. For angular simple harmonic motion, alpha is angular acceleration. Alpha is equal to minus nu square into theta for angular simple harmonic motion. From this, alpha plus nu square into theta is equal to 0. This alpha is nothing but d square theta by dt square plus nu square theta is equal to 0. This is in case of angular simple harmonic motion, the differential form of angular simple harmonic motion. Next, the characteristic properties of a body executing simple harmonic motion. Characteristics. The characteristics of a body executing simple harmonic motion. First, amplitude. This amplitude is defined as the maximum displacement of a particle about its mean position is called its amplitude. Next characteristic, phase. Phase is that which explains about the state of vibration of a particle about its mean position. State of vibration of a particle about its mean position is called its phase. Then velocity, acceleration, time period, frequency. These are all the characteristic properties of a particle executing simple harmonic motion. In detail, we will discuss about the relations of all these characteristic properties for a particle executing simple harmonic motion. Next, let us suppose that y1 is the displacement of a particle which is given by a1 sin omega t. Let y2 be the another displacement of a particle which is given by a2 sin omega t plus phi or theta. Then the resultant displacement according to the principle of superimposition theorem is y1 plus y2, that is a1 sin omega t plus a2 sin omega t plus phi. After simplification, we get y is equal to a sin omega t plus alpha, such that a is equal to resultant displacement a is equal to under root a1 square plus a2 square plus 2a1 a2 cos phi. Here phi is nothing but the phase difference between the two displacements y1 and y2. Then if phi is equal to 0, if there is no phase difference between the two particles, then I can write y is equal to, then a is equal to a1 plus a2 sin omega t. On the other hand, if phase difference is pi, then a is equal to a1 minus a2 sin omega t. These are the two different conditions. Now we shall get the formula for velocity. You know, velocity is equal to the differentiating distance with respect to time. So v is equal to, the formula for velocity is omega root a square minus y square. Here omega is angular velocity, a is amplitude and y is displacement. At mean position, displacement of the particle y is 0. So velocity is equal to a root omega root a square minus 0. That is omega root a square. From this, the formula for maximum velocity is a omega. That means the velocity of a particle executing simple harmonic motion is maximum when the particle is at a mean position. Then at extreme position, displacement of the particle is maximum, which is amplitude. If we substitute y is equal to a in this equation, we get v is equal to omega under root a square minus a square. That is v minimum is equal to 0, which suggests that the velocity of a particle is minimum in simple harmonic motion when the particle is at extreme position. Acceleration is defined as the rate of change in velocity. So the formula for acceleration is we have to differentiate v is equal to omega root a square minus y square. When you differentiate this equation with respect to time, we get the formula for acceleration as minus omega square into y. Now at mean position, displacement of the particle will be 0. Substitute y is equal to 0 in this equation. Therefore, a minimum is equal to 0, which suggests that acceleration of a particle is minimum in simple harmonic motion when the particle is at mean position. After that, at extreme position, displacement y is equal to maximum displacement amplitude. Substitute y is equal to a in this equation. Therefore, a maximum is equal to minus omega square into a. So acceleration is maximum for a particle executing simple harmonic motion when the particle is located at extreme position. After this, expressions for velocity and acceleration, then time period. Time period t is equal to 2 pi under root displacement by acceleration. That is the formula for time period. After time period, frequency. Frequency is nothing but reciprocal of time period. So what happens to the relation for frequency then? 1 by 2 pi under root acceleration by displacement. So these are the expressions for time period and frequency, which are the characteristics of a particle executing simple harmonic motion. This is under linear simple harmonic motion. For angular simple harmonic motion, time period t is equal to 2 pi under root displacement is angular displacement. by acceleration is angular acceleration alpha. This is time period. So, what happens to the frequency then? Frequency is 1 by 2 pi under root alpha by theta. So, these are the relations for time period and frequency. Potential energy is U is equal to half k y square. Here k is m omega square. Therefore, potential energy is half m omega square y square. This is the formula for potential energy. Now, at mean position, displacement is 0. Therefore, potential energy will be 0. That is, when the particle is at mean position, it will be having minimum potential energy. Next, at extreme position, displacement is maximum, which is amplitude. Therefore, potential energy is maximum, which is given by half m omega square a square. So, potential energy of a particle is maximum given by half m omega square a square when the particle is at extreme position in simple harmonic motion. So, after potential energy, the formula for kinetic energy. What is kinetic energy formula? Kinetic energy is equal to half m v square, but formula for velocity in simple harmonic motion is omega root a square minus y square. Now, substitute v as omega root a square minus y square here. We get kinetic energy as half m omega under root a square minus y square whole square. So, formula for kinetic energy is half m omega square into a square minus y square. This is the formula for kinetic energy. Now, at mean position, since the displacement of the particle is 0, kinetic energy is half m omega square a square, which is maximum. So, the particle will be having maximum kinetic energy when it is located at a mean position. Next, at extreme position, the displacement of the particle is maximum, which is amplitude. What happens to its kinetic energy? Kinetic energy is half m omega square a square minus a square. Therefore, kinetic energy is 0, which is minimum when it is located at extreme position in simple harmonic motion. The total energy T is equal to potential energy plus kinetic energy. That is, total energy is potential energy is half m omega square y square plus half m omega square a square minus y square, that is kinetic energy. That is half m omega square y square plus half m omega square a square minus half m omega square y square. These two terms cancels. Therefore, the formula for total energy of a particle executing simple harmonic motion is half m omega square a square. This is one of the relation to calculate total energy, and moreover, since omega is equal to 2 pi by t or 2 pi into n, because frequency is the reciprocal of time period, substitute the value of omega as 2 pi n in this equation. Therefore, one more formula for total energy, half m 2 pi n whole square into a square, that is half m 4 pi square n square into a square. 2 cancels here twice. Therefore, one more formula for total energy is two pi square m n square a square. This is one more expression for the total energy of a particle in simple harmonic motion. Oscillations of mass of a loaded spring means we consider a string, let some load be attached to the string, then what happens to its oscillations? As you can see here, a spring to which some load of mass small m is attached, either in this fashion or let a certain mass be attached to a spring. In this case, the oscillations of loaded spring are T is equal to 2 pi under root m by k. As that is the formula for time period, what happens to the frequency then? Frequency is a reciprocal of time period, that is 1 by 2 pi under root k by m. So, these are the relations for time period and frequency of oscillations of a loaded spring. Let us suppose a spring having a force constant k. In order to elongate the spring from x1 to x2, some work should be done. That amount of work done in elongating a spring is given by W is equal to half k into x2 square minus x1 square. This is the formula to calculate work done in elongating a spring from x1 to x2. Then the relation between spring constant and number of turns, they both are inversely proportional to each other, so that k1 n1 is equal to k2 n2. Here k is a force constant or spring constant of both the springs, and n1 and n2 are number of turns. n1 n2, they are number of turns. Two springs having force constants k1 and k2, they both are connected in series. In this case, the effective force constant is given by 1 by k is equal to 1 by k1 plus 1 by k2. After taking LCM, k1 k2, this is k1 plus k2. From this effective spring constant k is equal to k1 k2 by k1 plus k2. This is the formula for effective spring constant when the two springs are connected in series. On the other hand, when two or more springs are connected in parallel, the formula is k is equal to K1 plus K2 plus K3 plus so on. That is the formula for effective spring constants when the two or more springs are connected in parallel. Time period of simple pendulum. Time period of simple pendulum. The formula to calculate the time period of a simple pendulum is 2 pi under root L by G. So, very important one. Time period of simple pendulum is 2 pi under root L by G. Here L is length of the pendulum, G is acceleration due to gravity. Okay. Next, from this equation, how time period and length they both are related, T proportional to root L, squaring on both sides, T1 square by T2 square is equal to L1 by L2. From this T1 square L2 is equal to T2 square L1. This is also called law of lengths. Law of lengths. Then how time period and gravity they both are related, time proportional to 1 by root G. From this T square proportional to 1 by G. From this T1 square by T2 square is equal to G2 by G1. G2 by G1. From this T1 square G1 is equal to T2 square G2. This is law of gravity. First one is law of lengths, next is law of gravity. Now look at this equation, T is equal to 2 pi under root L by G. Here 2 pi is a constant, at a particular place the acceleration to gravity is also constant. From this equation it is evident that the time period of simple pendulum depends only on length of the pendulum. If the length of the pendulum is increased, time period increases. If length is decreased, time period decreases. Fractional change in length is dl by L, then fractional change in time period is dt by t is equal to half in dl by L. That is a fractional change in time period in terms of fractional change in the length of the pendulum. Then percentage change in time period is dt by t into 100 is equal to half dl by L into 100. That is a percentage change in the time period. Fractional change in gravity at a place is dg by g, then fractional change in the time period is dt by t is equal to half dg by g minus half dg by g, because the time period and gravity they both are inversely related. Now percentage change in time period in terms of gravity is dt by t into 100 is equal to minus 1 by 2 dg by g into 100. This is a fractional change in the time period of a pendulum in terms of fractional change in acceleration due to gravity at a given place, which is suspended in a lift. The formula for pendulum which is suspended in a lift, the time period t is equal to 2 pi under root L by g plus a. This is the condition when lift moves upwards with acceleration a. When the lift is moving in upward direction with acceleration a, in that case this is the formula to calculate time period. T is equal to 2 pi under root L by g plus a. As this is the time period, what is the frequency formula in this case? Frequency is reciprocal of the time period, that is 1 by 2 pi under root g plus a by L. The formula for frequency when the lift is advancing in upward direction with a uniform acceleration a. Next, one more condition, t is equal to 2 pi under root L by g minus a when the lift moves downwards with uniform acceleration a. When the lift is moving downwards with uniform acceleration a, this is the formula for time period. As this is the time period, what is the frequency then? 1 by 2 pi 1 by 2 pi under root g minus a by L. So, the formula for time period and frequency when the lift is advancing downwards with a uniform acceleration. Now, we shall have a look at some of the problems in this chapter, simple harmonic motion. First one, when the displacement of a particle in simple harmonic motion from mean position is 4 centimeters, then force acting on it is 6 Newton. Find the force when displacement is 6 centimeters. The given options are 3 newtons, 16 newtons, 8 newtons and 9 newtons. Look at the problem. When the displacement of a particle in simple harmonic motion from the mean position is 4 centimeters, the force acting on the particle is 6 newtons. You are asked to calculate the force acting when the displacement of the particle is 6 centimeters. So, what is the relation between force and displacement F proportional to x? From that F1 by F2 is equal to x1 by x2. Given F1 as 6 newtons, F2 you are asked to calculate, x1 is 4 centimeter, x2 is 6 centimeters. So, substitute the values in this relation. So, 6 by f2 is equal to 4 by 6. So, when you simplify that, you will get f2 as 9 newtons. So, the fourth option is correct one. The acceleration of a simple harmonic oscillator is 1 meter per second square when the displacement from the mean position is given as 0.5 meters. You are asked to calculate its frequency. The given options are, first one root 2 pi hertz, next pi by root 2 hertz, third 1 by root 2 pi hertz, and the last one as root 2 by pi hertz. Now, what is the formula for frequency? Frequency is 1 by root 2 pi under root a by y, that is 1 by 2 pi under root acceleration, it is given as 1 meter per second square. So, 1 by y displacement, what is the displacement given? 0.5. So, how much you are going to get? 1 by root 2 pi hertz. So, the option third one is correct one. The displacement x of a simple harmonic oscillator varies with time as a function as d square x by dt square plus 4x is equal to 0. You are asked to calculate time period. Here the given options are, first one pi by 2 seconds, the second one as a pi seconds, third one as a 2 pi seconds, and the last one 4 pi seconds. What is the differential form of acceleration of a particle executing SHM? D square x by dt square plus omega square x is equal to 0. That is the differential form of acceleration of a particle executing simple harmonic motion. Here given omega square, when you compare this equation with that equation, omega square is equal to 4. From this omega is equal to 2, but we know time period t is equal to 2 pi by omega, that is 2 pi by omega is 2, that is pi seconds. Therefore, the time period is pi seconds. So, the second option is a correct one. The velocity equation is given as under root 144 minus 16x meter per second. Here x is expressed in terms of meters. You are asked to find the maximum velocity. The given options are, first one 6 meter per second, second one 12 meter per second, third one 16 meter per second, and the fourth one as 8 meter per second. So, the formula for velocity is given where expressed in terms of meters. We are asked to calculate maximum velocity. Now, what is the general form of acceleration velocity of a particle executing simple harmonic motion? First, see here, given velocity as 144 minus 16x, that is a given equation. Comparing this equation with v is equal to omega under root a square minus x square. When you compare this equation with a square minus x square, this equation can be written as, since v is equal to under root 144 minus 16x, it can also be written as 4 under root 3 square minus x square. Now, compare these two equations. When you compare these two equations, we get omega as 4 units and amplitude as 3 units. Now you are asked to calculate maximum velocity. What is the formula for maximum velocity? V maximum is equal to A omega. A is 3, omega is 4. So 12 meter per second. So the second option is the correct one. Once again look at the problem. That is a given equation. You are asked to find the maximum velocity. In order to calculate maximum velocity, for my convenience, I am reducing this equation. V is equal to under root 144 minus 16x as 4 under root 3 square minus x square. Now, comparing this equation with original form of acceleration of particle executing simple harmonic motion as V is equal to omega under root a square minus x square. When you compare these two equations, in place of omega I am having 4 here, in place of amplitude 3 and x as it is. So I get omega as 4 units, amplitude as 3 units. As you are asked to calculate maximum velocity, the formula for maximum velocity is A omega. So substitute the values and simplify, you will get the answer as 12 meter per second. Next problem. The velocity of a body executing simple harmonic motion at mean position is numerically equal to the acceleration of the same particle which is at extreme position. You are asked to find the time period of particle. The given options are: first one pi seconds, second one 2 pi seconds, third one pi square seconds, the last one as 4 pi square seconds. Look at the data given. Velocity of a particle at mean position is numerically equal to acceleration at extreme position. What is the formula for velocity? V is equal to omega root under root a square minus y square. At mean position, y is equal to 0. So maximum velocity is a omega. The formula for acceleration is a is equal to minus omega square into y. According to the data given, at an extreme position, acceleration A max is equal to, at extreme position substitute y is equal to a here, we get omega square into a. He is saying that velocity at mean position is equal to acceleration at extreme position. As velocity at mean position is equal to acceleration at extreme position, I can equate these two equations. Therefore, omega square into a is equal to a omega. Cancel a on both sides, omega on both sides. So from this, omega is equal to 1. But what you are asked to calculate? Time period. Since time period t is equal to 2 pi by omega, 2 pi by omega we got it as 1. So the time period of oscillation is 2 pi seconds. Once again have a look at the problem. The velocity of a body executing a simple harmonic motion has mean position at mean position is numerically equal to acceleration at extreme position. You are asked to calculate time period. The formula for velocity at mean position is a omega. On the other hand, the acceleration at extreme position is a omega square. So according to the given condition, velocity at mean position, acceleration at extreme position, they both are equal. So I am equating those two equations by cancelling the like terms on either sides. I got the value of angular velocity as 1. As you are asked to calculate the time period, the formula for time period t is equal to 2 pi by omega. Substitute the value of omega here as 1. I am getting the value of time period as 2 pi seconds. So second option is the correct one. A body of mass 1 kg has a displacement varies according to the given equation y is equal to 8 cos 100 t plus pi by 3 centimeters. You are asked to calculate its maximum potential energy. The given options are, first one 8 joules, second one 10 joules, third one 24 joules, and the last one has 32 joules. Now, solution given, what is the expression for displacement? Y is equal to 8 cos 100 t plus pi by 3 centimeters. That is the given expression for displacement. As you are asked to calculate maximum potential energy, the formula for maximum potential energy is equal to half m omega square a square. So, compare this equation with that. Half mass is given as 1 kg, then omega square y is equal to a cos omega t plus phi. So, omega you are getting as, when you compare this equation with half m y is equal to a cos omega t plus phi, you are getting the omega as 100. So, omega square means 100 square, and the displacement is 1. Displacement is how much it is? 8 by 100 whole square. So, when you simplify that, you are getting the answer as potential energy as 32 joules. So, the second option is correct one. Once again, have a look at the problem. For a body of mass 1 kg, the expression for displacement varies according to the function as y is equal to 8 cos 100 t plus pi by 3 centimeters. You are asked to calculate its maximum potential energy. So, when comparing this equation with original form of a displacement, y is equal to a cos omega t plus pi, you are getting the angular velocity omega as 100 and pi as 8 by 100. As you are asked to calculate maximum potential energy, the formula for maximum potential energy is half m omega square a square. By substituting the given data, mass, omega, angular velocity and amplitude in this relation, and doing the simplification, you are getting the answer as 32 joules. So, according to the given options, the fourth option is correct one. The kinetic energy of a particle is given as 4 joules when it passes through its mean position. The mass of the particle is given as 2 kg with amplitude 1 meter. You are asked to calculate its time period of revolution. Now, the given options are, first one pi by 2 seconds, second one pi seconds, third one 2 pi seconds, and the last one as 4 pi seconds. So, kinetic energy is given as 4 joules. It is passing through mean position. As we already know that when the particle is at a mean position, which energy is maximum? Kinetic energy is maximum, potential energy is minimum. So, according to the problem, mean position kinetic energy, at which kinetic energy is maximum. What is the expression for maximum kinetic energy? Kinetic energy is equal to half m omega square a square, which is given as 4 joules according to the given data. So, from this cross multiply, m omega square a square is equal to 8. What you are asked to calculate? Time period. The formula for time period is 2 pi by omega, where omega is angular velocity. So, for that sake we need angular velocity first. So from this expression, omega square is equal to 8 by mass into a square. From this, omega is equal to under root 8 by m into a square. That is, omega is equal to under root 8 by mass is given as 2 kg and amplitude is 1 meter. So 1 square, that is under root 8 by 2, that is root 4, that is 2, which implies angular velocity is 2 units. But what you are asked to calculate? Time period. Since t is equal to 2 pi by omega, 2 pi by omega, I am substituting the angular velocity as 2, they both cancels. So you are getting the time period as 5 seconds. Second option is correct one. Once repeating the problem once again, look here. The kinetic energy of a particle is given as 4 joules at mean position. If mass of the particle is given as 2 kg with amplitude 1 meter, you are asked to calculate time period. So kinetic energy at mean position, he said. So for a particle executing simple harmonic motion at mean position, the kinetic energy is maximum. That formula for maximum kinetic energy is half m omega square a square, which is given as 4 joules according to the problem given. So half m omega square a square is equal to 4. From that, m omega square a square is equal to 8. From this, omega square is equal to 8 by ma square, omega is equal to 8 under root 8 by ma square. Substituting the mass as 1 kg, amplitude as 1 meter. When you substitute and simplify, you are getting the angular velocity as 2. As you are asked to calculate time period, we know time period t is equal to 2 pi by omega. Substitute the value of omega and cancelling 2 in numerator and denominator, we are getting the value of time period as 2 seconds. Second option is correct one.